welcome back for today's class. So we will continue with the welding section. So till the last class we have discussed about the metallurgical changes, what happens during fusion welding of different metals and composites, etc. And also we have discussed about the different principles of welding assisted phase transformation. So, to carry on the discussion today in this class, so we will start with the contact angle based discussion regarding wettability of the the weld melt generated at the weld pool in case of fusion welding. So, how the work of adhesion determines their integrity, the joint strength and also the structural integrity of the joint. So, we will talk about all three different processes, that is brazing, soldering as well as adhesive bonding. So they are basically grouped together in the as solid liquid state welding. So, the work of adhesion between a liquid and a solid is governed by the surface free energy according to this relation. So, this is the work of adhesion WADH is equal to the surface energy of the solid vapor interface. So, you can see over here, this is basically the surface energy of the solid vapor interface, this is the surface energy of the liquid vapor interface, and this is the surface energy of the solid liquid interface. Okay. So, assume this is the base metal, and where this is the melt pool which is getting generated, that means this is the liquid which is getting generated. So, so here for a liquid drop in contact with the solid surface having a contact angle alpha. So, if we take a basically balance the surface energy terms at this point, considering it as the origin. So, then what we will get? So, sigma delta S V, that means the lambda S V, that is the surface energy of the solid vapor interface, is becomes equal to the delta L V cos alpha plus delta S L. That means, so because there is an included angle, so we are basically taking the cos component, so that we can balance it with the surface energy of the solid vapor interface. And in the case of condition for full wetting, that is cos theta is equal to cos 0 degree. So, in that case we can get that sigma S V is becomes equal to lambda S L plus delta L V 0. So, here V 0 represents a saturated vapor. So, thus for a good wetting delta S V should be large. So, that is what we can draw from here. So, you can understand this concept if you what we have discussed earlier during the basics principles of solidification. So, it is very much similar to that. So, 0 degree angle means it is wetting completely, and then that in that case the nucleation becomes much faster, and virtually the barrier for nucleation vanishes. And also so this is the you can understand this from the concepts of homogeneous and heterogeneous nucleation that we have discussed earlier. So, going ahead, so the strength of a typically brazed joint varies with the thickness of the joint as shown here in this figure. So, you can see from here, so there is a optimum thickness of the joint where we can get the maximum strength of the joint. Why it is so? Because if assume that this is the these are the two plates that you are joining by adhesive joining technique. So, this is the adhesive. So, if after a certain thickness, so generally what happens, the strength of the joint there is a contribution from both the parent bodies which are getting joined. For example, these are the parent bodies A, B, they are getting joined by adhesive bonding technique. So, that contribution of the joint strength will come from A and B until a certain thickness, say T, and when the joint strength thickness say T1 it becomes T. So, then it is gradually decreases, the joint strength decreases, and after a certain higher thickness it becomes reduced to the strength of the filler material, which is otherwise always it is lesser than the parent body which are getting joined by the adhesive bonding technique. So, that is what is mentioned over here. So, for a very large thickness of the joint, the strength of the joint approaches that of the brazing alloy. So, this is true for brazing, this is true for adhesive bonding and most other welding techniques. So, below the optimum thickness, the entire joint is not filled up due to the strong resistance against the capillary flow. So, hence the strength is low due to the lack of a perfect fit. So, I mean, we have discussed about the reason why when the joint thickness is increased significantly, then there is a decrease in strength. However, beyond the, I mean, before reaching that optimum thickness of the joint where the joint strength is maxima. So, here this is the sigma max that we are getting. So, before reaching that joint thickness also, if we go with the lesser thickness of the joint, we have seen that the joint strength is below the sigma max. Why it is so? This is because of the lack of, for capillary flow of the, the filler material to completely fill the joint, it needs a certain gap, it needs a certain thickness between the joint. So, until that thickness is reached, the strength is lower. So, that is the reason that there is a optimum joint thickness which exists in case of brazing and also in case of adhesive bonding as well, that we will discuss next. So, in case of adhesive bonding, it is most used in the aircraft and automotive industries where sheet metals are joined in various configurations. So, it is it is kind of a semi permanent joint, I would say, because adhesive bonding, the plates or the parts which are joined together, they can also be separated when subjected to intense appropriate temperature and also appropriate force is applied to separate them. So, this is because in this case the metallurgical transformation is not involved. So, atomistic level bondings are not developed. So, that is why it is possible to be separated. Of course, there is a certain limit till which it is successfully withstands the applied in service loading conditions. So, that is why it has got widespread popularity in case of aircraft and automotive industries where sheet metal joining is a matter of concern. So, in this case, unlike in brazing and soldering, there is no uncertainty about the flow of the adhesive in the joint. This is so because the adhesive is first applied on the surfaces and the joint is made with subsequent application of heat and pressure. So, what this line means? So, because as we have discussed at the top that in case of brazing, in the capillary action the filler material needs to fill this gap, the joint region between the adjacent neighboring plates. Whereas, in case of adhesive bonding, so it is basically applied over the individual plates that are going to be joined with each other, and after applying the adhesive material, then there is appropriate pressure and temperature is applied to cure that adhesive and also to apply pressure on that adhesive, so that they can develop mostly the adhesives are polymers, so that they can develop appropriate polymeric chains and bondings between the upper and lower layer, between the adjacent layer which are getting connected to each other and which are. So, so that because of that here there is not uncertainty is not there. So, that is why in this case the joint thickness, that means we just have discussed about a optimum thickness that is needed in case of brazing, that is not a concern or that is not a constraint in case of adhesive bonding. Okay. So, in the case of adhesive bonding there are two types of bonding forces that take part in an adhesive joint. So, number one is van der Waals force due to the constant movement of the positive and the negative charges of molecules, and the other being the polar force, which is between the adhesive and the relatively brittle oxide film. So, due to the dipole adhesive molecules. So, this force is normally several orders of magnitude higher than the van der Waals force. So, hence this is the force which is more which is dominating in case of depicting the quality of the joint which is produced by adhesive bonding technique. So, the factors that affect the strength and the other mechanical properties of such a joint are the nature of and dimensions of the joint. The strength of a lap joint increases with the overlapped area and reduces with the joint thickness. So, So, this is the concept that we have just discussed, I mean just discussed earlier. So, here in this case also the why we are saying like this. So, lap joint, as we have discussed earlier, unlike the butt joint, here we are basically joining the adjacent plate parts or plates in the overlapped surfaces between the adjacent parts or plates. So, that is why as the surface area increases, that increases the strength of the lap joint. That means, adhesive bonding is always a lap joint, because it needs a greater surface area for the adhesive to achieve their to provide enough strength to the joint. So, and similar to the concept in case of what we have discussed just in the previous slide, that is, there is a, with the increasing thickness, the strength of the joint reduces because of the contribution from the adjoining plates or parts diminishes, and the strength reduces to the strength, mechanical strength of the joining material, the filler material or the adhesive which is applied in this case. It reduces to its own tensile or the mechanical strength. So, that is why with increasing thickness, the joint strength also gets decreases in case of adhesive bonding. And number 2 is the contact angle between the solid liquid interface. So, in the joint there is always a possibility of an air bubble getting trapped in the melt cavity and the adhesive melt cavity. So, the radius r of the bubble is determined by the size and shape of the cavity together with the contact angle phi. So, it can be shown that the tensile stress necessary to propagate a crack from the cavity is given by this expression, that is sigma t is equal to pi E A delta A by 2 r 1 minus nu A square to the power half. So, here E A, V A and delta A are Young modulus, Poisson's ratio. So, it will be nu A, so please correct it, it is not V A, and delta A are Young modulus, Poisson's ratio and the surface energy respectively of the adhesive material. And then so this is basically the case where the entrapment of air bubble within the adhesive layer which is used for development of the adhesive bonded joint between the adjacent plates is shown, which is having a radius r, and it is making an angle, included angle phi, that interface of the bubble with the adjoining solid adjoining the adhesive layer with the central axis. So, so moreover the stress concentration factor due to the formation of a meniscus. So, as we have talked about the entrapment of a bubble, so that will also form a meniscus within the adhesive body. So, the maximum stress concentration factor increases continuously from about 1 to 2.3 as phi increases from 0 to 90 degree up to a value of phi, that is, if phi is less than 30 degree, the maximum stress concentration factor and the failure both occur in the body of the adhesive, and beyond phi is equal to 30 degree, the maximum stress concentration factor and consequently the failure shift to the interface. Okay. So, the so this is what the concept of meniscus formation is shown over here from this schematic. So, the residual stress and the stress concentration. So, the adhesive in the joint shrinks due to both cooling and polymerization, and this shrinkage results in residual tensile stress in the adhesive and consequently reduces the strength of the joint. So, hence it is recommended that we do not superheat the adhesive material much, because with much superheat the chances of shrinkage and also the chances of residual stress generation within the adhesive applied between the adjoining metal plates will increase, and that will cause higher chances of a micro crack formation within the joint, and that in turn will significantly reduce the strength of the adhesive joint or the adhesive bond that has been developed between the adjacent plates. So, So, if a lap joint of two metal sheets of equal thickness T, so this is what is shown over here, and they are joined by the adhesive bonding route is considered. So, in this case it can be shown that the stress concentration factor in shear due to dissimilar materials can be given by this factor K, which is equal to C square G A by 2 E T into T A to the power half. So, what is G A here? G A is the shear modulus of the adhesive, and T A is basically the thickness of the joint. That means, this is the adhesive layer which is placed between the adjoining metal plates, and T, small t, is the thickness of the adjoining plates. Here it is assumed that both the plates which are getting joined by the adhesive bonding route are having same thickness small t, and E is the Young modulus of the metal plates which are experiencing adhesive bonding. So, here the factors, that is shape and bending of the adhesive, also gives rise to the stress concentration, and as and when the stress concentration between the adhesive layer increases, it causes it decreases the structural integrity and also the longevity of the joint, because as I told you earlier that adhesive bonding, the joint is a semi permanent nature, because the adjoining metal plates can be separated without causing any metallurgical changes between the adjoining plates, because at the onset of appropriate temperature and the mechanical force which is needed to overcome the strength of the adhesive layer. Okay. So, now we will move into the details about the weld metallurgy. So, assume that this is a plate A and this is a plate B, and they are basically getting joined with the help of at butt welding route. So, here basically a butt joint is getting formed between these adjoining plates A and B, and so here this is a backup plate, that is C, which is placed at the base of this adjoining metal plates, and then this is a electrode, which is electrode material, which is also a filler material. Often, like we have discussed earlier also, in case of arc welding, we will go into the individual arc welding routes where we can understand more about it. So, this is the filler material D. So, it like as a small recap, this filler material will be of having same chemical composition with the base material when we will talk about homogeneous welding, and it can be of different chemical composition when we talk about heterogeneous welding. So, this is basically the weld nugget or weld joint that is formed between the adjoining plates A and B. So, then when the filler metal is added, so the composition of the joint, the weld pool which is formed and then solidifies at the at the adjoining location of the original plates, the combination will be, the composition will be a combination of A, B, the back plate C, and also the filler metal D. Why it is so? Because this is a case of fusion welding, where there is fusion of both the adjoining plates which are experiencing joining, that has to be, because there has to be some metallurgical bonding and atomistic bonding needed to be formed, then only that, because welding fusion welding is a kind of permanent joint. So, we never intend to separate out the parts which are experiencing the joining between each other. So, that is why it has to be a metallurgical bond has to be developed at the adjoining region, at the weld zone. So, the total composition is a combination of A, B, backplate C, and also the filler material D. Okay. So, it can be also understood, fusion welding can also be understood as a casting within a large metal mold. So, but only difference is, because in this case, like in case of casting, for example, casting of a cylindrical billet, we have discussed that generally the solidification starts from the wall that is opposite to the direction of the heat removal. But in this case, because there is plate placed at the bottom, so here the structure formation, even if it is cellular structure I am drawing here, but it can be dendritic also based on the cooling rate involved. So, it will start from both the walls and also from the base. So, that is a different, and then the shrinkage pipe formation towards the end at the central location if the joint is not designed properly and if the filler material is not adequate. So, this is a difference, slight difference with the casting, but otherwise the procedure is quite same with the casting. So, moving on. So, so this is a typical grain structure and various zones are shown in case of a fusion weld. So, basically this is a case of double V bar joint. Please recall that we have discussed in the former class also that when we have to deal with a bigger joint thickness, then in spite of single V we often resort to double V configuration. So, in this case, so this is basically the root region of the welding, where these the adjoining plates say A and B, they are closest to each other, and this is the V joint which is prepared, where the filler material, if it is used, or the the molten metal which is generated because of the localized melting of these adjoining plates A and B, which gets drained and gets collected in this weld pool, and weld there basically. So, so this is the region where we can see much finer grains because of rapid solidification and cooling rate involved in this region, and there is a adjoining region like it is shown over here. So, this is basically the heat affected zone. So this is the HAZ heat affected zone, and this is the weld zone, and this is the parent metal or base metal. Okay. So, there is a large difference in microstructure that takes place in these three regions of the weld joint. This happens because of the differential cooling rate and differential thermal gradient that is experienced by these different zones of the weld joint. Okay. So, moving on, we can discuss. So, the metal in the fusion zone is cast material with a microstructure reflecting the cooling rate of the weld, as I discussed with you. So, this region cannot be expected to have the same properties and characteristics as the wrought material being welded, since their processing histories and resulting microstructures are largely different, and adequate mechanical properties therefore can only be achieved by selecting filler rods or electrodes which have properties in their as deposited condition that equal or exceed those of the wrought parent metal. Okay. So, this is because it can be understood from the, say, assume that this is a cold this is a cold worked metal, and we have elongated grain structure in this cold worked workpiece, that is basically in both the plates. So, which are experiencing joining with each other, and so the moment we are basically doing trying to get fusion welding between the both. So, that so there this structure gets lost, and we basically generate a melt pool which solidifies with a much higher cooling rate. So, generally the grain structure becomes much finer in this region of the weld pool compared to the grain structure that is present already in the base metal, and moreover the shape of the grains and their morphology is largely different than the shape of the grains present in case of the original workpiece. So, that is why the mechanical properties also varies significantly, and also there are so it depends if we take a if we draw a center line over here, and then if we draw a distance. So, along the, so say assume that this is the distance d and this is the say strength sigma. So, then so strength value basically it depends, the variation depends mostly based on the whether it is there is the it is a pure metal or it is basically the alloy that is experiencing the fusion welding process. But generally if it is a joining between two cold worked piece of metals or work pieces, then generally the strength basically increases from the center line like this. So, till it achieves the location till it enters the parent metal. So, likewise. So, this is how the strength variation happens if we study the variation of the strength of the material from the midway of the joint to till it enters into the parent or base metal. Okay. So, however, this strength I mean this is the normal case when we are talking about autogenous welding, that means when it is basically the melt pool which is formed because of the melting of the parent metal itself. But there are occasions where we are adding filler materials from outside, like in case of heterogeneous welding, when we are specifically using filler rods to create the melt pool. So, in that case, I mean, in that case it may happen based on the composition of the filler rod that we are basically using, it may happen the strength at the joint is even higher than the I mean than the parent metal which is getting joined. So, in that case the I mean nature of the strength versus distance variation will be likewise. So, in that case it can be, so anyway the strength of the I mean parent workpiece will always be same, I mean irrespective whether we are using filler material or not, but the joint strength will vary based on whether you are using filler material or not, or whether we are using a filler material which is having enhanced mechanical properties than the parent metal which is experiencing joining itself. So, the grain structure in the fusion zone may be fine or coarse, equiaxed or dendritic depending upon the type and volume of weld metal and the rate of cooling, but most electrode and filler rod compositions tend to produce fine equiaxed grain. Okay. So, now we will move into the heat affected zone. So, heat affected zone is basically the weakest region in a typical weld joint, which is I mean joined by the fusion welding route. So, again if I take the simplest example of a single V bar joint, which is I mean easier to explain. So, in that case, so this is the assume that this is the weld pool which is formed over here. So, this is the weld pool, and so then this is basically the heat affected zone. So, the heat affected zone is the region of the I mean joint where I mean when it is I mean it is under exposure to a high degree of temperature that is generated in the region of the weld pool. However, it does not experience complete melting, but it experiences thermal softening. If it is a precipitation hardened alloy, then the precipitates can get coarsened or it can show a over-edged structure. So, that is why normally the strength of this HAZ, the heat affected zone, decreases significantly, and it becomes the weakest link or weakest region of the weld joint formed between the adjoining plates, and thereby often it serves as the failure initiation site. I mean where from the I mean failure initiates in case of weld joint. So, so the in this region the parent metal has not melted, but it has been subjected to elevated temperatures for a brief period. Since the temperature and its duration may widely vary with the location, so fusion welding might be more appropriately described as a metal casting in a metal mold coupled with an abnormal and widely varying heat treatment. So, please focus on this statement. So, like in case of casting, first we are I mean solidifying the metal, and then we are basically subjecting it to heat treatment in case of precipitation hardenable alloys, where we can achieve improved mechanical properties by subjecting them to heat treatment. Whereas, in case of fusion welding, it is a simultaneous thing, like at some region it is the casting happening, and in other regions, for example, heat affected zone, there it is basically subjected to the parent metal which is experiencing joining are subjected to heat treatment. So, that is why I mean it is that above statement is mentioned here. So, because of this altered structure, the heat affected zone may no longer possess the desirable properties of the parent material, and since it was not melted, it cannot assume the properties of the solidified weld metal either. Consequently, this is the weakest region in the weld joint. So, often failures initiates from here. Okay. So, so the discussions whatever has been done until now has been I mean shown here schematically. So, this schematic if you follow, you can understand all the regions of a typical fusion I mean fusion welded structure. So, this is basically the weld pool. So, this is the weld pool where you can see the weld metal, and then this is the region where you can see the fusion zone. I mean it is basically the boundary of the fusion I mean weld pool, okay. And then this is the transformed I mean part of the heat affected zone, and this is the lower temperature part of the heat affected zone. So, even with so this as a whole is the heat affected zone originated due to the due to the fusion weld happened between these workpieces say A and B, but there the properties and microstructure largely varies within the heat affected zone also based on their exposure or proximity with the weld zone. Okay. So, that is what you are seeing here. Here the demarcation has been done nicely. So, here this is the transformed part of HAZ and this is the low temperature part of HAZ and this is the parent metal. Okay. And here you can see this is the initial edge of the joint, that is initially prepared, because beyond I have drawn several times for you that the the example of a single V bar joint. So, this dotted lines talks about the edges which are prepared initially for developing joint between the parent workpiece A and B, but during exposure to fusion welding either it is autogeneous or homogeneous or heterogeneous, whatever it may be. In that case, because of the exposure of the heat generated for weld pool creation in the joint. So, this is the this zone gets extended into the deep into the workpiece beyond the region where the edge is prepared initially. So, that is why this is marked as a initial edge of the joint, and then the finally the till what the weld pool extends within the parent body is marked here as the fusion line, and then this is the region where the transformation between the transformed part of the HAZ, the boundary between the transformed part of the HAZ and the low temperature part of the HAZ is termed here as the transformation line, and this one has been the farthest corner till which there is effect originated from the welding process that happened between two plates. So, that has been termed here as weld zone line. That means, it shows as it marks the boundary of the low temperature part of the heat affected zone. So, beyond this line there is hardly any exposure, hardly any effect of the welding process that happened between these two plates. So, that is why welding is a localized phenomena. If we are talking about large assembly, then the whole assembly, apart from the region where the welding actually takes place, there is hardly any effect that we generally observe. Okay. So, so this is basically the metallurgical changes of different zone of the weld joint. You can understand it better. So, you can easily correlate between these two. So, so because of the melting, solidification and exposure to a range of high temperatures, the structure and properties of welds can be extremely complex and varied. Processes with low rates of heat input, that is slow heating, tend to produce large total heat content within the metal, slow cooling rates, large heat affected zones and resultant structures with lower strength and hardness, but with higher ductility. Whereas, with high heat input processes have lower total heats, faster cooling rates and small heat affected zones. So, that is why what are some of the example of high heat input processes, we will discuss in detail about them later. However, for your knowledge, I can take the name of laser beam welding, electron beam welding. So, there they are talking about high heat input in a highly localized manner. Because of their localized impact, the joint becomes much cleaner and the heat affected zone size also gets reduced significantly, and apart from the region where the joint formation is necessary, it hardly impacts the metallurgical structure of other regions of the parent body which are experiencing joining with each other. So, so the size of the heat affected zone also what high size of the heat affected zone can increase with increasing starting temperature, decreased welding speed, increased thermal conductivity of the base metal and a decrease in base metal thickness. So, so thermal conductivity also plays a big role, because it can transport the heat from the weld zone much faster to the parent body, and in that way it can if we are talking about slow welding speed, then the size of the heat affected zone can increase significantly, because of higher exposure time to the that high temperature that is generated at the weld zone. Okay. So, I mean, so that is why, I mean, so the, I mean, process conditions as well as the geometry of the joint, both are important to achieve the joint with the desired structural integrity and the desired microstructural and mechanical attributes. Okay. So, how to change the properties of weld and its structure? So, if the as welded properties are not acceptable, then what we can do? We can subject the weld joint to heat treatment. So, what we can achieve there? We can similar thing like we have discussed in case of casting, we can achieve precipitation hardening and thereby we can increase strength, and in occasions we can also improve its I mean ductility, I mean formability. So, the entire welded assembly might be heat treated and the after welding. So, the structure variations can be reduced and eliminated, but the results are restricted to those that can be produced through heat treatment. So, the structure and properties associated with cold working, for example, could not be achieved, but it up to a certain degree we can minimize the compositional differences between the weld zone and the parent metal, and also we can improve on the strength and elongation properties of the weld joint. However, if there is a intrinsic defect like the defects which we have discussed in case of casting are also true in case of weld joint which is formed in fusion welding, such as I mean gas porosity or even slag inclusion, impurity entrapment. So, if these kind of defects are present, then it is very difficult to correct those by heat treatment alone. So, in that case we may even need to scrap the joint itself. So, then an alternative technique can be to reduce microstructural variation, or the sharpness of that variation can be to preheat the parent bodies which are going to be joined by a fusion welding technique. So, either the entire base metal or material at least 10 centimeter on either side of the joint just prior to welding can be preheated. So, this heating serves to reduce the cooling rate the joint experiences, and because of the reduction of the cooling rate, the chances of hot cracking and as well as cold cracking gets significantly reduced, which are one of the primary regions of failure of the fusion welded joint. So, so these are basically the remedies and precautions that one can take to achieve fusion welds with desired attributes and desired microstructural attributes and mechanical integrity. So, with this we are done with this class, and we will go into the details of weld design and the mechanics involved in case of the weld joint between the adjoining plates when they are joined along the edges, when they are joined along the surfaces, and also different kind of loading conditions these joints subjected to, how they behave. So, we will discuss all those in the next class. So, thank you for now.